So we've talked about using a chemical formula. How do we figure out what chemical formulas are? We can figure out an empirical formula from elemental analysis. We can take the masses of elements, we can take a compound and decompose it into its individual elements and weigh those and figure out what the masses of each element are. Or we can look at the masses of elements that react to form a compound. That's what we'll be doing in experiment 3. We'll react zinc and iodine and figure out the masses that react to form the compound, and then we can calculate the empirical formula. We can also do it from knowing the percent composition. So what we're getting here is the empirical formula. It's the ratio of atoms or moles of atoms. It's not the ratio of masses. So instructions for doing this. We need to start with the mass of each element present in a sample of the compound. Sometimes you're given the mass and then you just write it down. Other times, if you're given a percentage, the easiest thing to do is just assume that we're starting with 100 grams of the compound. And then the percentage is the mass, right? If it's 77% carbon, and you say, well, if I had a 100-gram sample, then I'd have 77 grams of carbon. So you can just trade the percent sign for a g gram, and you're ready to go. Next, we take the masses and we convert to moles of each element using the molar mass. Then we need the mole ratios, and so we're going to take the smallest number of moles, whichever element that is, and we're going to divide all of them by the smallest. Sometimes that gives us beautiful, nice whole numbers. Other times it's a little messier. This is my personal rule of thumb down here. Results within 0.2 of a whole number should be rounded to the whole number. So that means if you got 3.14, is that within 0.2 of the number 3? 3.14 minus 3.00 is 0.14. That is less than 0.2. So I can round this to 3. If it's not within 0.2 of a whole number, then we're going to have to do some other things. So if we don't get whole numbers, then we multiply all of those ratios by the same small whole number so that we get whole numbers. These are the fractional equivalents of the decimal equivalents of fractions. So 0.2 is 1/5, 1/4, 1/3, 1/5. And so, 2/5. If we multiply by these numbers, when we have this fraction at the end, then we'll get whole numbers. So if that makes sense to you, that's great. It can speed things up. You're like, oh, I know what to multiply that by. If that made no sense to you, then a trial and error method is almost as fast. Try multiplying by 2. Do you get whole numbers? No? Try 3. Try 4. Try 5. You should never have to go past 5. So let's do an example. Sample of a compound is decomposed in the lab and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Find the empirical formula. So we need to start with masses of the elements, and they gave those to us. So I'm going to write those down. 165 grams of carbon and 27.8 grams of hydrogen and 220.2 grams of oxygen. I can't find the formula with the ratio of masses. I need moles. So I have to convert these masses to moles. So I want moles of carbon. I'm dividing by grams. That number, the molar mass, is on the periodic table. 1 mole of carbon, 12.01 grams of carbon. So 165 grams of carbon divided by 12.01 is going to be 13.738555121. Again, we get lots and lots of digits there. It's important here to not round too much. If you round too much here, you can actually end up with the wrong formula. So keep at least the correct number of significant figures. Never go below that. I would keep an extra or 2. Here we've got 3 sig figs and 4, so we really should have 3 sig figs in there. I'm going to keep 2 extras, so I'm just going to dump the rest of these. Moles of carbon. So we're going to do the same process with the others. We got moles of hydrogen, grams of hydrogen. I look up the molar mass, it's 1.008. So I've got 27.8 divided by 1.008. Moles of hydrogen. And 1 mole of oxygen per 16 grams of oxygen. So the calculations themselves are pretty simple. It's just that we're having to do them multiple times, so it can get a little tedious. And I think really the hardest thing is to remember what you're supposed to do next. Because you get started calculating and then you get to the end of doing something and then you're like, oh wait, where was I going with that? Like you go upstairs in the house and you're like, wait, why did I come up here? I just did the stairs, yay, but why? So we have moles of each element. We're trying to find the empirical formula. We need the ratio of the moles. We could use these as subscripts. C 13.7, H 27.6, O 13.8. But those aren't whole numbers, right? The simplest way to get whole numbers is to identify which of these is the smallest number. It's this one. And we're going to divide all of them by that smallest. We want the smallest because then all of our numbers are 1 or greater. So this is going to give us exactly 1. $27.579 divided by 13.738. This is giving me 2.007. And this is giving me 1.002. Those are ratios, they don't have units. Are these close enough to the whole number that I can round them? Yeah, they're super close. So this is 2 and this is 1. You're always going to end up with one of them being 1. So those whole numbers are the subscripts in my empirical formula. So for the carbon, the subscript is 1. Do we write the 1? No, we don't. And for hydrogen, the subscript is 2. And then for oxygen, it's 1, so we just write the element. So that's the empirical formula. Any questions? Yes?
Is it in that specific order for a reason?
It is. It is in that specific order for a reason. I don't expect you to remember that. Bless you. They usually give you the elements listed in the order that they should be in their formula. So we don't really have to worry about it. But yeah, there is a reason. Any other questions? Here's our friend ibuprofen. This is my mom answer to everything. I sprained my ankle. Take some ibuprofen. I have a headache. Take some ibuprofen. Ooh, you've got a fever. Here's some ibuprofen. So I just think it's humorous that this comes up several times in the textbook. Drug of choice, right? Ibuprofen has the following mass percent composition, blah, blah, blah. What's the empirical formula? So here, similar problem and yet different. We're given percentages instead of masses. What we want to do here is say, well, I'm going to pretend I have 100 grams of this, because then I can just take this percent sign and make it into a gram, a mass. So I can just like, oops, that's too big. I can just make that go away and put a gram in there. And it's not magic, it's not cheating or anything. Although sometimes it feels that way. So we've got masses. We take our masses, we convert to moles, and then we find the ratio. So 76.69 grams of carbon. Well, I want to convert to moles of carbon. 1 mole, 12.01 grams. This time I'm going to keep the correct number of sig figs instead of keeping extras, and it should work out just fine.
What do you do with the 100 grams?
Well, I'm pretending I have 100 grams of the whole compound. And so then 75.69% of 100 is 75.69 grams. Mm-hmm. So my mass there has 4 sig figs, so I'm going to keep 4 significant figures in my answer here, and this 5 rounds up to a 6. So there I've got moles of carbon. .80 grams of hydrogen. 1 mole of hydrogen is 1.008 grams. 8.8 divided by 1.008. It's going to be 8.73 moles of hydrogen. 15.51 grams of oxygen. 1 mole of oxygen for 16 grams. Whoops, 16. And it says 375. The 3 is then going to round up to 4. Yes.
75 to 16.
Thank you. Yeah. I wrote 76 instead of 75, so that would be a problem. So it's 6.302. Thank you. Okay, questions? What do we do next? Divide by the smallest. We need to get whole number ratios. So here, this is the smallest one. When I divide that by itself, of course, I get 1. 0.9694. Sometimes it's tempting to just do this kind of in your head and round it off. It's dangerous. So this comes out to 9.006. 6.302 divided by 0.9694. This is going to give me 6.501. And I guess technically this should only have 3 sig figs, so we'll fix that if we want to. So can I round all of those to whole numbers? Can I round 6.5 to a whole number? Is this within 0.2 of a whole number? No, it isn't. If I was going to round that, I'd round it to 7, right? So if I take 7 and subtract 6.501, is that less than 0.2? Well, it's greater than 0.2. That's 6.5. It's right between 6 and 7. I can't round that. If I round it, I'm going to end up with the wrong formula. So 0.5 is the decimal equivalent of 1/2. And if I don't recognize that, I'm still going to try multiplying by 2 to see what happens. So if I take 6.501 times 2, oops, I get 13.002. Can I round that to a whole number? Sure. That's really close to 13. Now, the ratio is 6.5 to 9 to 1. I can't change it and make it 13 to 9 to 1. If I multiply 1, I have to do it to all of them, so the ratio stays the same. So if I multiply this one, I'm going to get 18.02. Well, I can round that to 18. And then this one times 2 is going to give me 2. So the formula is going to be C13H18O2. Yes? Yep. Yeah, if I multiply 1, I have to multiply all of them. Because what I got before multiplying was C 6.5, H 9O. And so this is the correct ratio, but they aren't whole numbers. So I multiplied all the subscripts by 2, and then I get C12, C13, H18O2. That's the smallest whole number ratio. We can't go any smaller because 13 is an odd number. So the ratio is 13 to 18 to 2. That's the lowest whole number ratio. We want whole number ratios because this might be the molecular formula, and if it's the molecular formula, it has to be whole numbers of atoms because it's like the 2.3 children in your family. That might be the average family size, but you can't have 2.3 children, right? Any questions? So that's how we find the empirical formula. How can we figure out what the molecular formula is? Well, we do need one more piece of information. We need the empirical formula and the actual molar mass of the compound. In a problem that's going to be given to you, they're going to say, well, here's stuff so that you can calculate the empirical formula, and the molar mass of the compound is this. The molecular formula is the empirical formula multiplied by a whole number, a positive integer. That could be 1, in which case the molecular formula and the empirical formula are the same. It could be 2 or 3 or 4. The empirical formula is the lowest ratio, and the molecular formula gives us the actual ratio. So the way we find out what that number n is we take the molar mass of the compound that they tell us, and we're going to divide it by the molar mass of the empirical formula. We've got our empirical formula, we calculate that molar mass, and see how many times does that fit into the actual molar mass. And that tells us what to multiply all of our subscripts by. So a compound has an empirical formula, CH, and a molar mass of 78.11 grams per mole. What is the molecular formula? So the empirical formula is CH, and the actual molar mass is 78.11 grams per mole. What is the mass of the empirical formula? Well, we can calculate that, right? There's 1 carbon and 1 hydrogen. So that's going to be 13.018 grams for every mole. This is smaller than the actual molar mass. So the molecular formula is not the same as the empirical formula. How do I figure out how many times bigger it is? I use division. 78.11 grams per mole, divide by the mass of the empirical formula. And this should always give you a pretty good whole number. If it doesn't, you've got a mistake somewhere. So this is giving me 6.00015, some other digits. That's 6. So this tells me that the molecular formula is 6 times bigger than the empirical formula. And so I'm going to multiply all the subscripts by 6, and I'm going to end up with C6H6. This has the empirical formula CH, and if I calculate the mass of this, it's going to be 78.11, or very close. .108. Any questions? So we talked about a couple of ways of determining the empirical formula by measuring the amounts of substances that form or the amounts of elements that form when you decompose the compound. Another way is combustion analysis, and this is a very common technique used especially for organic chemicals. Organic compounds typically contain carbon, hydrogen, and oxygen. So when you burn a compound containing carbon, hydrogen, or oxygen, all of the carbon gets turned into carbon dioxide. All of the hydrogen turns into water, and then we can find the mass of oxygen in the original compound by subtraction. So if it contains carbon, hydrogen, and oxygen, and we can figure out how much carbon and hydrogen are there, and we know the original mass of the sample. We take the original mass minus carbon and hydrogen, and that gives us the mass of the oxygen. So here's a schematic of an instrument for determining this. So you'll have some sort of a furnace here with your sample. So you weigh the compound and you stick it in there, and then there's oxygen, and this gets heated and ignited, and as it burns, all of the gases that are given off go out in this direction, and they go through a series of tubes. The first tube has a substance in it that absorbs water. So the water vapor that's being produced here is going to get stuck in this material. So they weigh the tube before and they weigh the tube after. It's heavier, and the difference in mass is the mass of water that was given off. The gases then go through the next tube, which absorbs CO2. And again, you compare the mass before and after, and you can figure out the mass of CO2 that was given off. And then anything else, and the extra oxygen is just going to go straight through. Any questions about that? So to find the empirical formula from combustion analysis data, it gets a bit messy. It's very, very easy to get lost. And so this kind of a problem, and there will be one on the exam, this kind of problem, you want to make sure that you're writing everything out and being really clear. And especially on an exam, it can be helpful to actually give yourself a list of things, a set of instructions, literally write them on the exam of what I need to do, right? So that you don't forget once you get in the middle of it. So what we need to do in order to find the empirical formula is first we need to find the masses of the elements, right? Here the problem is telling us that this one contains only carbon and hydrogen. So I need the mass of carbon and I need the mass of hydrogen. What I'm given is a mass of CO2 and a mass of water. But we just learned how to figure out the mass of an element in a given mass of compound. It's a little tedious, but I never claimed that science was not tedious. Science can be extremely tedious, as can any aspect of life, right? Sitting in traffic waiting for the train to pass. Tedious, yeah. So I'm going to take this 1.60 grams of CO2, and I want to find out the mass of carbon in that. So I can go from mass of this compound to moles of the compound. And then using the information in the formula, I can figure out moles of carbon. And then I could go to mass of carbon. Well, let's think about this for a minute. After I get my masses, what am I going to do to calculate the empirical formula? The first thing is to calculate the moles. Well, that's right here. So maybe let's just stop there. We'll just stop there with the moles, because we need the moles, and then we can do the mole ratio. So down here, I need grams of CO2, so those cancel out. And I'm going to have moles of CO2 down here, so those cancel out. How many moles of carbon in a mole of CO2? One. 1 mole of carbon per mole of CO2. And then I need the molar mass of CO2. So I've got 1 carbon plus 2 oxygens, so that's 44.01. So again, I want to keep at least 3 significant figures because that's what I was given, 0.0364. 2.4 moles of carbon. Better, I mean, more is better, but it can add to the tedium of all the little bits. So 0.819 grams of water. I'm going to find out how many moles of water, and then how many moles of hydrogen. And since ultimately I want the moles of hydrogen, I'm not going to go to grams, because then I'll just have to go back to moles. How many moles of H2O, how many moles of hydrogen in a mole of H2O? 2. It's right there in the formula. Then I need the molar mass of, let's do that a little better, of water, 18.016. I use that one so much I remember it. 0.819 divided by 18.016 times 2. Bless you. 0.909 moles of hydrogen. Now what do I do? I'm going to divide by the smallest so I can get ratios, right? So 0.0364 is the smallest. So that's going to give me 1. And this is going to give me something else. 0.0909 divided by 0.0364. This is giving me 2.497. Can I round that? No. That's basically 2.5, right? So I'm going to multiply this by 2 to see if I can get a whole number. Times 2, and then I get 4.9945. Can I round that? Yeah, I can call that 5. And if you're not sure about when you can round and when you can't, we'll talk about that together. So this would be 2. So then my formula, carbon 2, hydrogen 5. That's the empirical formula. Any questions?
So if it's containing oxygen too, then we do a second process for it?
Yeah, if there's oxygen, then it gets a little more complicated, and I think that's what's on the next slide.
Based on the homework assignment, I got that one wrong.
Yeah, it's trickier. Did you have a question?
So I just want to clarify. So on like the second step, when we have moles of CO2 and moles of H2O, that just means like the molar mass of 2 oxygens and 1 carbon, or 2 oxygens.
The conversion here?
Yes.
Yeah, so to convert from grams of CO2 to moles of CO2, I use the molar mass, and I just look at the formula, and I get the mass of 1 mole of carbon and 2 moles of oxygen. I add them together, and I get 44. Yep. Any other questions? Oops. Okay, so this one's going to be the one with oxygen in it. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produces 1.6004 grams of CO2 and 0.6551 grams of H2O. Find the empirical formula. So we need to get moles of carbon, moles of hydrogen, moles of oxygen. We can take the mass of CO2 and find moles of carbon. We can take the mass of water and find moles of hydrogen. But then the mass of oxygen we can't get from this, because in the process of burning that, we're pumping tons of oxygen in there. So this oxygen in these compounds, the water and the CO2, probably did not come from the compound. And if it did, it also has additional oxygen, so that's not going to help us out at all. But we can calculate the mass of carbon in here and the mass of hydrogen and subtract those from the original mass. And then we'll have the mass of oxygen, and we can calculate the moles of oxygen and get the lowest ratio. Okay. So 1.6004 grams of CO2. I'm going to do the same thing I did on the previous example, where I'm going to convert this to moles of CO2. And then to moles of carbon. Because there's 1 mole of carbon per 1 mole of CO2. I'm going to go ahead and write that number down because I want that number, but then I also have to go on and calculate grams. It's 1.6004 divided by 44.01. So this is 0.03. I've got 5 sig figs in the beginning there. 3, 6, 3, 6. My molar mass is only giving me 4, so we'll hope that this is good enough. That's moles of carbon. And then we'll go do the hydrogen from the water, 0.6551 grams of water, converting to moles of water using the molar mass, and then looking at the formula, seeing there are 2 moles of hydrogen per 1 mole of water. 0.6551 divided by 18.016 times 2. So this is 0.07272 moles of hydrogen. If the compound only had carbon and hydrogen, we could take those moles and do a ratio. But there's oxygen also, and so we need to figure out how much oxygen was in there. So to do that, I have to find the mass of carbon. I had the moles of carbon, so I have to convert this to grams of carbon. So 0.03636. Those are just kind of fun numbers, aren't they? This is 0.4367 grams of carbon. And converting moles of hydrogen, 1.008 grams of hydrogen per mole of hydrogen. 0.07272 times 1.008 equals, this is 0.07330 grams of hydrogen. I need to do that so that I can find the mass of oxygen. So I had 0.8009 grams of the compound, and I can subtract the mass of carbon and subtract the mass of hydrogen, and what's left is my mass of oxygen. 8.009 minus 0.4367 minus 0.0733 equals 0.2909 grams of oxygen. but I need moles of oxygen. So I'll take my mass of oxygen and I'll convert it to moles. And I get 0.01818 moles of oxygen. So now I've got moles of carbon, moles of hydrogen, moles of oxygen. Now I can divide by the smallest, which is the 0.01818. So this one is going to give me 1. This is going to give me 4. And that's giving me 2. So 2 moles of carbon to 4 moles of hydrogen to 1 mole of oxygen. Empirical formula. And that's a big, bad, ugly problem. But it's made up of simple pieces, right? What makes it hard is putting them all together in the right order, remembering what to do. Any questions?